Hello everyone, welcome back to your channel where we discuss physics problems. But today I am not going to discuss any specific problem. Today's video will be about semiconductor and few concepts about their doping properties. So let's start. Okay, let's draw a rectangular specimen of semiconductor material and let's consider it. This is a silicon material. Okay, so it has a length from x equal to 0 to x equal to else. As you all know that semiconductor is basically crystalline in nature in most of the cases. There are amorphous materials, semiconductor materials also, but in general we consider semiconductor crystalline. Now in crystalline material the atoms are periodically arranged. So these are the silicon atoms which are periodically arranged here. I am not drawing all those atoms. So let's extend this. Okay, this is the pristine or pure semiconductor. Okay, pure silicon semiconductor. Now silicon has valency of plus 4, and if I dope this material with element which has valency less than 4, then it will result in p type doping. So if I dope with boron, which is a trivalent atom, then it will result p type doping. P type doping. And if you dope with a pentavalent atom like arsenic, then it will give result of n type doping. Now why this doping is necessary? So semiconductor is a material which has conductivity in between metal and insulator. So now for technological advancement, sometimes we need to tune the conductivity. Just by external doping, we can change the conductivity of semiconductor material in a large range. Okay, so that's why this doping is very helpful in that context. Now, let's see a particular type of doping, N type doping. So, this is a silicon atom. It has valency 4. So, covalent bonds are there in silicon crystal. Okay, okay. We know that sp3 bonding, sp3 hybridization is there, and the crystal structure is diamond cubic structure. So basically the valence is 4. Okay, now if I incorporate a arsenic atom and substitute this silicon with this arsenic atom, so in the whole lattice there will be few atoms that will be substituted with this external impurities. Uh, so silicon is replaced with the arsenic, and it has 4 bonds with the neighboring silicon atoms. Now 4 valence electrons are used in covalent bonding. Okay, and there is a extra electrons that is attached with the nucleus. This is not initially free. There is some sort of attraction, but now if thermal energy is provided, this bond will be broken. Okay, and this electron will be free. Now this free electron will move inside this whole lattice, and there will be conductivity. This is free electron, and it will rise conductivity. Now As we dope with more arsenic, dopant concentration if you increase, then the free electron will be increased and the conductivity value will be increased. Okay, fine. So now let's draw the band diagram. So this is the conduction band, this is the valence band, and this is the forbidden energy gap, the band gap. For silicon, this is 1.1 electron volt. Now I am drawing this as a line, but basically it will be a band, and I am just showing the edge of this band. And similarly here there is another band, valence band. Now when arsenic is placed in the silicon crystal, then there will be a dopant level. Okay, this is the donor level, ED, and this is the ionization energy. So these are fine. Okay, now initially there will be arsenic as a neutral atom, and when it will give a free electron, so the arsenic will be as a positive ion. Okay, now let's think a scenario. Think of a scenario here. Let's now let's think of a scenario here. There is a silicon semiconductor. Okay, and I am doping it with arsenic, but the doping is not uniform. With the distance, the doping concentration is changed, and let's take the doping concentration is like this. At x equal to 0, the doping is low, and at x equal to L, the doping is maximum, and this profile is linear change. Now, what will happen? So, I have shown that whenever arsenic is doped inside the silicon crystal, so there will be a free electron, and also the arsenic will be as a positive ion. That's fine. Now, my question is, I haven't attached any external bias. So, will there be any electric field, or will there be any current? These are the concepts I want to address here. Okay, so let's think of it, and I am also telling this what is happening here. So here arsenic doping concentration is small. So at this position there will be a positive ion. This positive ion concentration will be less, and here doping concentration is high, arsenic doping concentration. So this positive ion concentration will be also high. Okay, so here arsenic plus one will be, this ion will be more in comparison to here. Now you know that when there is a positive charge here, more positive charge, and here is a less negative charge, so the electric field will be from the more positive to the less positive. Okay, so here more arsenic ions are there. Okay, so the field will be from this direction to this direction. Okay, from right to left. Fine. So although I haven't given any bias, but there is electric field. So we know that from Ohm's law, what it tells, J equal to sigma E. When there is electric field, there should be associate current density. So this the material show any current, any conductivity. So what will happen? Let's think. So one thing is that this is in equilibrium. When I haven't applied any bias, there will be no current, but it indicates that there is a current. So basically this is the drift current, because drift current is from the arises from the electric field. Okay, and this drift current will be balanced with the diffusion current. So this is the reason why there will be no net current. Although there will be an electric field, net electric field, that will be from this direction that I have shown from right to left, but there will be no net current. So the concentration of arsenic is here more, and the concentration of arsenic is here less. So here, here, okay, more free electron concentration is more. Here free electron concentration is less. So the as we know that if the in a room, if I spray deodorant, and then the molecule will be spread from the higher concentration to lower concentration. So there will be a current, diffusion current. So here in the same case there will be current. Okay. So that these two currents, that J drift and J diffusion, will be opposite, and they will balance each other, and finally there will be no net current. Okay, so this is the case. Hope this video helps you to get some concept from the semiconductor doping. And if you find it worth this, then please like it, and if you haven't subscribed yet, please subscribe the channel. And thank you, take care.